Hello, today I'll be presenting our work, a deep learning based non-intrusive parametric reduced order models for high Reynolds number airfoil driven flows. Regarding the motivation for this work, in our earlier works, we have been using such high fidelity CFD solvers in order to assess the performance of turbines. However, these solvers cannot be used for a fast digital twin platform because they are computationally expensive to run. An alternative to this is developing reduced order model of such flow solvers. However, one approach that we are using is non-intrusive reduced order models, or also called as NEROMs. And these NEROMs have shown good potential at low Reynolds number. However, they need to be tested on high Reynolds number flows. Hence, this is the motivation of for our work, and we want to fill this knowledge gap. We want to see how the neurons perform on high Reynolds number flows, and for this purpose, we have used a NACA 0015 airfoil because airfoil shapes serve as a foundation for wind turbine blade design. So it's a good starting point, and we run it at high Reynolds number of 10 raised to 5 or 10 raised to 6 Reynolds number, and the NEROM generally development is done in two stages. One is offline stage, during which we develop the NEROMs, and an online stage during which we use NEROMs to generate flow fields for new values of parameter. Now let's see how these stages are done. Now in the offline stage, we first generate database. We conduct lots of simulations. About nine simulations have been done with varying Reynolds number. Here Reynolds number is our parameter, and the Reynolds number is varied from 320,000 to 1.2 million. So these are quite high Reynolds number, and these 7 Reynolds number are used for training, and then the NEROM. And finally, we test the NEROMs on intermediate Reynolds number like 640,000 for interpolation case, and for extrapolation 160,000 Reynolds number. Now, why this problem could be a very challenging test case is because at these high Reynolds number, we observe tremendous change in flow pattern due to with change in Reynolds number. Like for a Reynolds number of 320,000, we see the wake structure is like this. It's shedding like this. Wakes are there from the airfoil. While at 1.12 million, the wake is completely different. And at 640,000, the wake is again very different. So with change in Reynolds number, the flow patterns and the wakes are different, even though they are in the turbulent regime. But because of the levels of intensity of turbulence, the boundary layer separation varies, and the wake patterns and the flow patterns varies. So our objective was to test whether NEROMs can generate this flow pattern for an unseen Reynolds number of 640,000. Once we train it using Reynolds numbers between 320,000 to 1.12 million. So now once we have generated this database, the next step is we do POD based decomposition, where we decompose the data into orthogonal spatial modes and accompanying temporal coefficients. Now, in case of typical reduced order models, we select just a few basis functions that can capture most of the variance in the flow. And then using these few basis functions and their associated temporal coefficient, we can reconstruct the flow field. So it's called a reduced model. While in our non-intrusive reduced order model, what we do is we use a long short-term memory, which is a variation of recurrent neural network, to try to learn this dynamics of this temporal coefficient. So this long short-term memory neural network is able to predict the temporal coefficients at any given time based upon its previous values. So LSTM is able to we try to make the LSTM learn this temporal coefficient dynamics for a given mode. Now all the parameters used in this study, like dropout, activation function, epochs, batch size, look back, all these things, this we obtain using a hyperparameter optimization routine and a software called as Optuna. And once this LSTM is trained, we use it to in the online phase. So in the offline phase, we obtain the basis functions for the known values of Reynolds number and a LSTM model that can predict the temporal coefficients. Now in the online stage, we obtain fields for new unseen parameter. And to do this, to obtain the fields, we need to know the spatial basis functions for new parameter value, which we obtain using interpolation. And this interpolation is based on Grassmann manifold and its tangent space. So we try to obtain spatial basis functions for Reynolds number of 640,000. And this is compared with the POD basis generated basis functions on the actual data. So here we can see that there are some similarities and there are also some differences. And this could be attributed because the Reynolds, with the change in Reynolds number, the flow fields or spatial even bases are changing quite a lot. And so the interpolation is giving lots of similarities, but also some differences. And regarding the associated temporal coefficient with these basis modes, we use, as said, we use the trained LSTM model. Now, once we obtain the basis functions and the trained LSTM and the temporal coefficients, we can reconstruct the flow field. However, we would like to share some of the knowledge that we got while training this LSTM. When we started training the LSTM with with the database from just 2 Reynolds number and tested it on 640,000, then we saw that there is some deviation between the predicted, that is the LSTM predicted, the red ones, and the actual true values. There is some predictions, deviations, and also it's not able to capture the oscillations. So these are different modes, and for each mode, this is the temporal coefficient associated. So then when we trained it with more larger database with 7 Reynolds number for same 640,000 case, we obtained that now its LSTM learned a lot. It started performing better. It also started to capture the temporal dynamics, oscillations. But we can still see that there are deviations. And when we try to think about why these deviations could be there, even though it's trained with best of hyperparameters and thing, then when we try to put the current LSTM performance in perspective, then we see that it could be related to challenging physics that changes a lot with the parameters. Like for example, we compare high Reynolds number airfoil, that is our current work, which is up at 10 raised to 5 or 10 raised to 6 Reynolds number, with a case of low Reynolds number vortex merger case that's operates just at 200 to 800 Reynolds number. So vortex merger is there are two vertices that merge together and with time. And when we try to see the physics of when we try to see the temporal coefficient with time associated for a given mode of this vortex merger case, we see that with change in Reynolds number, that is from 200 to 800, from blue to red line, there is a pattern here which is visible to the eye. So, but in case of airfoil, that is our current work, when we are trying to predict for RE 640,000, that is this purple line going through here, and we see that this with change in Reynolds number, the change in the temporal coefficient dynamics with time, it changes in a pattern which is not discernible to the eye. Like we cannot make out if there is a pattern, if it is there with our normal visual inspection. Hence, in order to unearth the pattern, the LSTM has to undergo intense training, and then this can influence how it performs. Like here, in this case, when we do the LSTM, train the LSTM using the solid lines and test it on the purple line, then we see that the LSTM blue and purple line, they are that is LSTM is predicting very close to the true one. While in this case, the current airfoil case, there is these deviations that are there despite the best efforts at training it. So this is because we perhaps need more training data, more parameters, so that this dynamics is it's able to capture accurately. But anyways, it's still able to capture the trend very well. And when we finally reconstruct the flow, its impact can be seen. Here we see that flow reconstruction is perfect between non-intrusive ROM and true fields. While here we see that this is the true field full order model, and this is the LSTM GP generated NIROM model. We see that there are slight some deviations even though trend is captured, and this is the error one. And to zoom it, it's like this. And when we try to see the dynamics, that is, we go ahead from time t equal to 0, then we see that the LSTM GP norm is able to capture the wake size and wake pattern to quite a similar to that of a full order model here. And even though there is some difference in the far wake, the dynamics is slightly different, which is because of the uh, uh, challenging case it is. So overall, we can conclude that NIROM has shown its ability in capturing the qualitative trends with change in parameter at high Reynolds number when it is within interpolation range, and it has shown scope in improvement with more data sets. This potential, the potential that it has shown and the scope paves the way for future research on NIROMs. And thank you.